We're going to do two-dimensional collisions. Two-dimensional collisions can be elastic, where energy is conserved, or inelastic, where energy is not conserved, depending upon how inelastic the collision is. You can see that these objects are going off at angles. So one of the things you're going to need when we're solving problems is what angles these things roll off to after collisions. So one of the best ways to figure this out is by, solving a problem. So first off, we're going to look at our red object colliding into our green object. And over here on the left is before the collision. We have the velocity initial of the red ball before the collision. It's going at 5 meters per second. We have the mass of the red ball. We have the velocity of the green ball and the mass of the green ball. Velocity of the green ball, interestingly, is 0. It doesn't always have to be 0, but in this case, we are having this initial velocity of the green ball be 0. Uh, and in here we have the angles that each ball shoots off at. So the red ball is going off at a 33-degree angle, green ball is going off at an 18-degree angle. So first thing we're going to do is understand that momentum is conserved in the x direction and the y direction. So all the momentum that these objects have in the x direction before the collision is the momentum they should have after the collision in the x direction. And same thing for the y direction. So we've set these up for x and y components. So for the initial momentum of the red ball in the x direction plus the initial momentum of the green ball in the x direction has to equal the finals in the x direction. And the same thing would go for our y components. Added up on the left, the initials have to equal the finals. A couple of these that we can eliminate from our calculations based on the information we have is, first off, we know that the initial momentum of the green ball, the initial momentum of the green ball is 0 because its velocity is 0. So this and this both should equal 0. And the red ball only has velocity in the x direction initially. So the initial velocity of the red ball in the y direction is 0, so that makes the momentum 0. And you're left with two equations that look like this. Sorry, we should erase that. Two equations that look like this. Now, we have 1, 2, 3, 4 unknowns. 4 unknowns. And we want to reduce those down. So we need to do our trig to reduce those down, and we'll do our trig to put these components into their vector term without the x or y components. And what we have is, the momentum vector for the red ball has x and y components. That's going at 33 degrees. And we know that cosine of 33 is adjacent over hypotenuse. So adjacent over hypotenuse, we've just multiplied the hypotenuse over. So we have something to substitute in for our x component of the final momentum for the red ball. And same thing with the y, except we're using sine because sine is opposite over hypotenuse. And the same thing goes for the green ball. We're going to use cosine of 18 for the x and sine of 18 for the y component. And it's negative here because our y component in the green for the green ball is going in a negative direction. So we have to identify that as negative. So we do that here. And then we can plug in uh, our variables. And when we plug these in, we have 1, 2 unknowns. Now we have reduced it down to 2 unknowns. And we can solve for, sorry, got distracted, had to pause the video. So where were we? We've reduced ourselves down to 2 unknowns, and now we can solve for one side and plug it into the other side of the equation. I'm going to start calling my PRF, the momentum of the red ball, final. We're going to call X. So we have X, and our Y component, our Y is going to be the PGF. We're going to replace that with Y. So we can see we've got 2 unknowns, 2 equations, and we can solve that. So I'm going to isolate the Y over here, and we can see that Y is going to be equal to X sine 33 over sine of 18. That's just isolating the Y. We're going to take that and plug it in over here. When we combine these two equations, we get 6 equals X cosine 33 plus, substituting this in for Y, X sine 33 sine of 18 times, don't forget the cosine that is attached to this Y. And when we multiply out and do the math, you will solve and find that X is equal to 2.38. And we can take that X, plug it into either one of these equations, and solve for Y, and we get Y is equal to 4.19. So, again, our X was the momentum final of the red ball. So that's equal to 2.38 kilograms times meters per second. And the green ball final is equal to 4.19 kilograms times meters per second. Now that we have both momentums, we can figure out what the velocities for each of these are. The velocity of each ball. The momentum final for the red ball, again, is 2.38, and that's the mass of the red ball times the velocity of the red ball final. That's equal to 2.38. We know the mass of the red ball is 1.2, so solving for VF, V final of the red ball, we will get 1.98 meters per second. And do the same process over here for the green ball, and you're going to find that the velocity of the green ball final is equal to 5.99 meters per second for our final velocity for the green ball. Why we want these is, the reason why we want these is because we're going to determine whether this is an elastic or an inelastic collision. And the way we find that is plug it into our conservation of energy equation and see whether the initial energy equals the final energy. Doing that would look like this. So we only have to deal with the kinetic energies because we're assuming that the potential energies cancel out because these things are acting at the same height. So expanding the initial kinetic energy, we've got the mass of the red ball times the velocity of the red ball initial squared all over 2. Mass of the green ball times velocity of the green ball initial squared over 2. And that has to equal mass of the red ball times velocity of the red ball final squared over 2 plus mass of the green ball, velocity of the green ball final squared over 2. So the kinetic energies initial have to be equal to the kinetic energies final. And we have all of these variables, so we can plug them in and solve. $15 is the initial kinetic energy of the red ball. 0 is the initial kinetic energy of the green ball. 2.35 and 12.6 of the red and green ball, respectively, with their kinetic energies after the collision. And we add them up, and we'd get 14.95 joules, which rounds to 15 joules. So your energy is conserved. Uh, so if energy is conserved, we know this is an elastic collision, and we can look at all our numbers, and you can look at them on your paper as I run this uh, collision simulator. We're going to move this to an elastic collision. We have 15 joules of kinetic energy. Show the values, our speeds before the collision and after the collision. After the collision, we have 2.0 for our velocity. We calculated 1.98. And the speed after the collision for the second ball, we calculated 5.99. So we're pretty darn close. Our momentums were 2.38. This is the simulator showing 2.39, and we had 4.19. It's 4.2 on the simulator. One of the discrepancies with the simulator and our work, obviously rounding and also maybe not the exact same angle between the two.